Hello everyone and welcome back again to the linear algebra component of the calculus and linear algebra series. In the last video we introduced this idea of the orthogonality of two vectors in Rn, and we also talked about some properties of the scalar product in Rn. And in this video we want to introduce this idea of projections of one vector onto another. So what do I mean by that? Well, what's quite useful here is to draw a picture. So let's consider a picture in R2 because that's what allows us to kind of draw this geometric idea. So let's take one of our vectors as this yellow vector here, say. Let's say we call this vector here v. And suppose we've got another vector that I'll draw along here that we can think of as, we'll call this u. And I want to say, effectively, how much of u, of the vector u, is contained within the vector v. So, in other words, if I project v down onto this vector u, how much of the component of u in this direction is in v, right? Because we can see that v is somehow composed of something, a vector going along in this direction and in this direction, and we want to know how much of v is in this direction. And that's our idea of the projection. So drawing it and where this projection idea comes from is we take this, the kind of tip of this arrow here, we bring it down, and we put the tip of that arrow here, where this is kind of in our direction u, and this red arrow now is what we think of as our projection. So we label this thing here now as the projection of v onto u. That's what we write in this way. And this thing here in this vertical direction, going up here, doing this green arrow, is what we actually call the orthogonal projection of v onto u. And the reason why we call it the orthogonal projection is we see that this blue vector here is perpendicular or orthogonal to this vector, or in turn we see that it's orthogonal to this vector here. These two vectors are indeed orthogonal. And we'll prove that in a moment when we kind of look at some explicit formulas for these. So how in R2 would you figure out what this projection is? Well, we can just use some simple trigonometry. So let's call this thing theta here, which is the angle between v and u. Then we can realize that this projection vector here, so let's write this as the projection. Maybe shift this over a little bit. So we can write the projection of v onto u is going to be what? Well, it's going to be whatever the length of this vector is, and we can figure out the length of this vector because it's effectively just going to be, by using some trigonometry, it's going to be the norm of this, the length of this one, times by cosine of theta. So we're going to get something like the norm of v cosine of theta, and then we want to multiply it by the vector in this direction, but we need to make sure that that vector has a unit length, right? Because if we pick u, if we pick this full vector here, u, and we multiply it by this thing, it's going to stretch it even further. So what we want to take is, here we've got the length of our projection vector, and we want to multiply by the unit vector of u. In other words, the unit vector of u is given by u divided by its length, its norm. But we can write cosine of theta using the dot product. So we can write this as the norm of v times by u dot v over the norm of u times the norm of v, because we know that from the definition of the scalar product, times u over the norm of u. Now we see here that this cancels, the norm of v cancels, and this thing just multiplies by this thing to square it. So in other words, we've got, make sure this can be seen, we have a u dot v over the norm of u all squared times u, but we can otherwise write the norm of u all squared as simply just u dot u. So this is sometimes written as u dot v over u dot u. We'll kind of bracket that and we multiply it by the vector u. So kind of this was our geometric picture, and that allowed us to figure out what this projection was, at least in 2 dimensions, and similarly we could extend it to 3 dimensions. So for our kind of definition in Rn, we're going to define the projection of v onto u as this equation here, because this thing generalizes to vectors in Rn, right? We can define the scalar product on both the top and the bottom, and then we just multiply it by another vector in Rn. So that leads to our definition. And let's write that explicitly. So we have, we want to let u and v be vectors in Rn. And we also want to have the condition such that u is non-zero, because there is going to be no component of v in the direction of the zero vector, because the zero vector is just simply a point. Then we say, then the projection of v onto u is defined as exactly what we wrote above. The projection of v onto u, we write it in this way, is equal to u dot v over u dot u times the vector u. And we can show that in an example that we have here in the notes. So I will go through an example. Let's say I've written 3 examples here in the notes, but I'll go through one of them. Let's just go through the first one. So we have our example. And in this situation, we let v equal the vector -1, 3, and u equal the vector 2, 1. Then we say the projection of v onto u is given by what? Our formula above, we write it as the projection of this lowercase u, so v onto u, this means is we want to write u dot v. So what's the dot product of u and v? That's going to give us -1 times 2 plus 3 times 1 all over, we write this now as u dot u, which in other words is 4 plus 1. And we times it by the vector u, which is 2, 1. So what does this thing give? Well, on the top, we've got -2 plus 3 over 5 times 2, 1. And then we've got 3 minus 2, which is 1. So in other words, we have 1/5 times by the vector 2, 1. So that's what we mean by the projection of v onto u. And there's some other examples there in the notes for doing it in R3, but it easily generalizes to Rn as well. Well, one of the important points now to go back to in our picture is we said here that we have this idea of the orthogonal projection. And we can also see from this picture, what's quite useful, is that all our vector v here can be always decomposed into its projection and its orthogonal projection. In other words, v is equal to the projection of v onto u plus the orthogonal projection of v onto u. We see that here because if we just go in this direction plus this direction, that's the same as this vector here, v. So it makes sense then that we should define our orthogonal projection, this thing, as v minus the projection. And that leads us to our definition of the orthogonal projection, which we'll write down here now. So we have our definition. As before, we let u and v be vectors in Rn. And because we want to define the projection, we need to have u is non-zero, or is not equal to the zero vector. Then we say, then the orthogonal projection and we're going to still do it of v onto u is defined as, write it as O, the orthogonal projection of v onto u is equal to v minus the projection of v onto u. And it's worth checking now that indeed this thing is orthogonal, that this vector here is indeed orthogonal to this vector, right? Hence the definition. So what does it mean to say that these two things are orthogonal? It would mean to show that we can show that the dot product between this vector and this vector is equal to 0. So that's going to be our theorem, and that's where we're going to prove that, and that's where we're going to finish off. So theorem is that if we have the usual, we take let u and v be vectors in Rn such that u does not equal the 0 vector, then we have that the orthogonal projection of v onto u dotted with the projection of v onto u must be 0. In other words, those two things are orthogonal. So let's prove this. Well, it suffices, right, to show that rather than just looking at the orthogonal projection, which is rather than just looking at the projection, which is a slightly nastier formula, we can just dot this with the vector u, right? Because we see that the projection here is in the same direction as u. So if we can show that the dot product of this with u is equal to 0, then it would be, we can conclude that the dot product of this and this is equal to 0. So it suffices to show that the scalar product of this and this is equal to 0, and that will complete our proof. So let's write that down. It suffices to show that this vector, the projection of v, the orthogonal projection of v onto u, is orthogonal to u. So that is, if we take the orthogonal projection of v on u and dot it with u, what is that going to equal? Well, we can use the distributive property of the dot product that was proven in the last theorem, that's going to give v dot u, right, because this thing here is v minus the projection of v onto u, and then it's going to be minus, and then we want to write the projection formula, so that is u dot v over u dot u, all times by u dot u. And we can see here that because these things are scalars, these things cancel, so these are just going to be real numbers. So we get v dot u minus u dot v. But we also know that the scalar product is commutative, as we proved in the last video. So these things are equal to one another. In other words, this thing is equal to 0, and hence, therefore, we're done, because we've shown that the orthogonal projection is orthogonal to the vector u, and because this vector here, the projection of u, v on u, is in the same direction as u, it follows that this thing must equal 0. So that's where I think we're going to conclude this video. And in the next video, we're going to talk about a notion of a product on Rn, well, in particular, a vector product on R3, because it turns out we can't define products like we can do with additions in Rn for every single value of n. There's actually a very kind of restrictive number of cases in which we can define these products. And you might have seen these before, known as the cross product. So once again, I remind you to read the notes and kind of analyze any of the proofs and some of the material that we've talked about in this video, and attempt any problems in the module handbook pertaining to the material covered. So thanks very much for watching, and I'll see you in the next video.